Ferry wheels is an example of circular motion. A loop of the roller coaster could be an example of circular motion. So the circular motion that we're learning here is a uniform circular motion. Okay, uniform circular motion means the object will be moving with constant speed, but it will have acceleration. Because the acceleration is due to the change of direction. The acceleration is always towards to the center of the circle. And this type of acceleration, we call it as centripetal acceleration. A uniform circular motion means object is moving in a circle with constant speed and it has an acceleration which call it as centripetal acceleration. And this acceleration is due to the change of direction. So centripetal acceleration is given as v squared over r. Centripetal acceleration is also can be written in terms of omega. Omega is angular speed. So AC, C stands for centripetal acceleration. And the direction of the centripetal acceleration is always towards to the center of a circle, right? So why AC is also equal to r omega squared? Because the relation between the V is actually linear speed or tangential speed. V is equal to r omega. AC centripetal acceleration is v squared over r, and V is equal to r omega. Therefore, V squared will be r squared omega squared. Therefore, AC is equal to r omega squared. That's how you get the AC as r omega squared. In the other word, AC is v squared over r. AC is also equal to r omega squared. Where omega is called as angular speed. Okay, now since we keep mentioning that centripetal acceleration is actually the acceleration due to the change of direction of the speed. So although an object is moving in a circle with constant speed, but the direction is changing, so we could calculate out the centripetal acceleration. But if the object is moving with not a constant velocity, right? So we can also find out the acceleration, and the acceleration is called it as tangential acceleration, right? Tangential acceleration is due to the change of the speed. Acceleration of the object is a tangential square plus a centripetal square, then square root of it. So this tangential acceleration is an acceleration due to the change or changing of speed. And acceleration, centripetal acceleration is due to changing of direction. For uniform circular motion, so uniform circular motion means the speed is constant, and therefore the A is referred only to AC. Okay, because the tangential component is equal to 0. So that's why now we focus on AC only. So we can also apply the Newton's second law for a circular motion. F equal to ma. So if you refer to circular motion, this A here is referred to centripetal acceleration. And the force here will refer to centripetal force. The Newton's second law, when applied for a uniform circular motion, you will have AC is v squared over r. So you will get mv squared over r. Or if you set it in terms of omega, you will have mr omega squared, because AC is equal to r omega squared. Okay, so this is actually Newton's second law. Okay. What are the example of actually the centripetal force? Example of a centripetal force would be the tension in the string from the top view, right? Let's say this is the object. So this is a vertical circle from the top view. Okay, and the tension of the string is actually referred to centripetal force. Okay, so this centripetal force is actually the resultant force. This is my pendulum. Then I swing it in a horizontal circle. Okay, so the string, this is the string. So the centripetal force is always towards to the center, right? So let's say the angle here is theta. So this T here, so again, in making the angle to the vertical, so this T can be resolved into T sine theta, where T sine theta is referred to centripetal force. And other than that, the tension in the string, gravity. Gravity, for example, basically centripetal force is a force. So this one is referred to gravity force, gravitational force. For example, a moon is always orbiting about the Earth. This is the Earth. And here is the moon. Moon is always orbiting about the Earth in a circular motion, right? In a circular motion. So there will be a force. So this is a gravitational force. It's also the example of a centripetal force. Okay? And the frictional force exists between the tires and the car to keep the car moving in a circular motion. Is also an example of centripetal force. We have a car moving in a circular motion. So this is, firstly, I draw out the free body diagram. This is a free body diagram of a car moving in a circular motion. I have the mg, I have the normal, and the static friction force that hold the car from sliding down, all right, or from slipping. Now I apply Newton's law. So vertical component. So applies Newton's law, F equal to ma. So vertical component means y and y. So there will be no acceleration along y component. So the net force is equal to 0. So this is summation, right? Net force. So what are the forces along y component? Normal and mg. So I take up as positive, down as negative. Then I will have n plus negative mg equal to 0. N is equal to mg. However, for horizontal component, so I have a horizontal component or x component. Okay, summation of fx equal to max, right? So ax, if the car is moving in this direction, yeah. So ax is actually the centripetal acceleration because the car is moving in a circular, right? In a circle. And ax is referred to mac. So why is it x? Because it's along x-axis and it is towards to the center of the circle. This is a center of the circle. So this fx is towards to the center of the circle, right? So summation of fx will be equal to the static friction force is equal to mac. There's only one friction force. I have fs is equal to mac. Okay, now the objective is I want to find out what is the maximum speed of the car so that the car will not sliding, right? It will still in contact with the road, right? So then I applied Newton's law on the horizontal component. And I also know that the maximum friction force here is actually, this one should be maximum, is actually equal to mu s multiplied with the normal force, mac. So what is normal force? So happen I already get the normal force is equal to mg. I substitute in and eventually you will get mu s mg is equal to mac. So what is mac? ac is v square over r. R will be the radius of the circle, right? So from here you can get m and n can be cancelled out. From here you can get the v is actually equal to mu s r g square root. And this one will be the maximum velocity of the car without slipping. We can also find out what is the minimum mu s required to hold the tire in contact with the road. From this expression, mu s is equal to v square over rg. So this is the minimum coefficient of static friction required to hold the tires on the road without slipping. Horizontal circle. Okay, say I have a pendulum, simple pendulum. I swing it in a horizontal circle. Okay, and it is making the angle of theta to the vertical. Let's say the ball is moving with a constant speed of v. Firstly, I draw out the free body diagram of this simple pendulum. So this t here can be resolved into t sine theta and t cos theta. So I can also label the mg of the ball, gravitational force acting on the ball, right? So now I apply Newton's law. So Newton's law is said that F equal to ma. So if I refer to horizontal component, so x component, horizontal, so this is x, this is x. Horizontal component of fx is always towards to the center, okay, which is a centripetal force. So this fx here is actually a centripetal force. So instead of fx, I write it as centripetal force is equal to mac. Centripetal force does not exist in the free body diagram. So this centripetal force, resultant force, it's just like this fx. Resultant force. And based on this free body diagram, so the resultant force along x component is t sine theta. So I will have t sine theta is equal to mac. So ac is v square over r. Okay, let's say the radius of the circle is r. It can be a capital letter of r or small letter of r. So this is x component. And however, for y component, okay, for y component, I will have summation of fy is equal to 0. So based on the free body diagram, so y component, there are two components here, t cos theta and mg. So we add up together, we will get t cos theta plus negative mg is equal to 0. T cos theta is then equal to mg. Maybe when the ball is here, so you can also draw the free body diagram. So here is the mg, and this is the t. Then the angle is still theta. So this one is t cos theta, and here is t sine theta, right? So if the ball is here, you can also refer back to the same expression. Okay, So it is because when the ball is here, the centripetal acceleration will be towards to the left. Towards to the left, centripetal acceleration will be in this direction. Okay, or I highlight it. Acceleration will be towards to the center of the circle. Right? When the ball is located here, it's towards to the center of the circle. So we always take the direction along the AC as positive. So when the ball is here, you take this as positive. That's why this component is still positive. Right? When the ball is on the left-hand side of the circle, and the centripetal acceleration will be towards the center. So we take this as positive. So T sine theta is still equal to mv squared over r. So it doesn't matter the ball is here or here. You will get back the same expression. Okay, next one, we look at vertical circle. I have a string tied up with a ball, then I swing it in a vertical circle. When the ball is at the top and when the ball is at the bottom. So when the ball is on the top, so the tension will be always away from the object. So this is the tension. So this is the tension, and always towards to the center. Okay, this tension is actually the centripetal force. You can also actually draw out on this location also. Okay, we have a few locations. Okay, let's say this is number 1, this is number 2, this is number 3, this is number 4. So at location 1, which is on top, summation of F is equal to MA. So this one is centripetal force. It's always toward to the center. So if you look at this diagram, okay, I have the mg as well. Mg is always directed downward. So at position 1, summation of force is actually equal to mg plus T. Centripetal force is mg plus T, the net force, and it's always toward to the center. So this at position number 1, I took pointed downward as positive. Okay, because pointed downward is towards to the center. So I always follow the direction of the centripetal acceleration, and you will get it as MAC, which is mv squared over r. R will be the radius of the circle. This one is r. Okay, at position number 2, so if I draw up the free body diagram, so mg will be here, always directed downward. Now we investigate on centripetal, so I know that centripetal force is along x-axis. This is along x-axis, so I take this as positive. Position number 2, towards to the left as positive, because AC is always towards to the center of the circle. Right? Centripetal force only exists along x-axis, or along the horizontal component, and this one is T is equal to mv squared over r. Okay, at position number 3, so I draw the free body diagram, mg is always downward. So at position number 3, I assume that up as positive. So because centripetal acceleration is towards to the center. Okay, so it's up as positive. Then the summation of F, C is equal to MAC. So I will get T plus negative mg is equal to mv squared over r. At position number 4, 4 is here. Okay, so I can also draw the mg here, but it is in a vertical component. So horizontal component means centripetal force, and therefore I have Fc equal to MAC. Okay, there's only one force, which is the tension force. So T is equal to mv squared over r. So where we take moving to the right as positive. Okay, so this is a few positions that you can apply. Okay, on the Newton's law at these 4 different positions. A vehicle moving in a vertical circle. This is an example of a vehicle moving in a vertical circle. Something like a roller coaster in a loop. It's also a vertical circle, right? But without the tension. So we'll investigate 2 positions on top and at the bottom. It's still vertical circle for a vehicle on a vertical track. Okay, so example is roller coaster. Okay, this is a circle. So we only consider two positions, yeah? Okay, when the roller coaster car is at the bottom, okay, you are sitting down here. Okay, so I draw the free body diagram. So you are sitting down here means there is a contact between you and the car. So there will be a normal force, and mg is always directed downward. Okay, so this is a bottom. At the bottom of the loop. So at the top of the loop, so you and the roller coaster will move together. So on the top of the loop, the car will be something like this, reverse, right? So your head will be here, but the normal force is actually will be downward. Mg is also downward. Okay, this is a free body diagram on top and at the bottom for a roller coaster. To avoid the passenger from falling down, the speed here must be very fast. So on the top here, a minimum speed must be applied. Okay, what is this minimum speed? So now we look at the free body diagram on top. N and mg is pointed downward. The centripetal acceleration is towards to the center. So towards to the center means going downward. So we assume that this one is positive, pointed downward as positive. Okay, I applied Newton's law. Summation of F is equal to ma. So this is centripetal force and centripetal acceleration. So I will have mg plus n equal to mac, or mac is actually mv squared over r. For example, the radius of the circle is r. When v is equal to v minimum speed, n is equal to 0. So which means when n is equal to 0, substitute inside this equation, mg plus 0 is equal to mv squared over r. So this v is called it as v minimum. So from here, v minimum is equal to square root of gr. Okay, and therefore, this is the v minimum that you must apply to the roller coaster to avoid the passenger from falling down. So which means if v is more than the v minimum, then the normal force is not equal to 0. So not equal to 0 means, oh, there is a contact between your buttock and the roller coaster car. All right, then you are safe. So at the bottom of the car, we can also apply this Newton's law. So bottom, so which is at this point. So when I apply Newton's law, summation of F is equal to mac. This force is a centripetal force. So now when the car is at the bottom, so we know that AC is always directed towards to the center. So towards to the center, when the car at the bottom is pointed upward, and therefore I use upward as positive. There are two forces, which is N and mg. So I assume up as positive, down as negative. So add up together, I will get N plus negative mg is equal to mac. So AC means v squared over r. So from here, you will get the normal force is actually equal to mv squared over r plus mg. There's another type of a vertical circle. Ferris wheel on a vertical track. This is a Ferris wheel. So you move together with the chair. So at the top, free body diagram will be different from the roller coaster car. Let's look at it. Draw out the free body diagram of a Ferris wheels on a vertical track. We will investigate on the top and the bottom as well. So at the bottom, the chair is something like this. So you are sitting down here. So when I draw the free body diagram, I will have mg downward and the normal force. So when the chair is on top, you will be sitting down like this. So the normal force is still on top, pointed up, and mg is downwards. Okay, so we are going to investigate on the top location and at the bottom location. So on top, we applied Newton's law. Summation of F is equal to ma. So force here will be centripetal force. On top, the acceleration is towards to the center, which is pointed downward. So I use on top, pointed downward as positive. So add up together, mg plus negative n. mg plus negative n is equal to mv squared over r, where r is the radius of the circle. So from here, the normal force at the top of the circle, circular motion is mg minus mv squared over r. So at the bottom, we applied Newton's law, F equal to mac. When the Ferris wheel is at the bottom, so the centripetal acceleration is toward to the center. Towards the center at the bottom here, it's actually pointed upward. So we assume that this is positive, and therefore, when I add up together all the forces, the resultant force, I will get n plus negative mg is equal to mv squared over r. So here, normal force is equal to mv squared over r plus mg. Right? You can see that the two equations, the normal force is actually different. One is mg minus mv squared over r. Another one is mv squared plus mg. So at the bottom, the normal force is higher.